So if you remove any subset of its edges of size less than k, the graph remains connected. For instance, here we have a 2-edge connected graph. You can see that the graph is connected, and if you remove any edge of this graph, it still remains connected.
Can you try to speak up a bit louder?
Okay, I'll try. So in the connectivity augmentation problem, as an input, we are given a k-edge connected graph G and a set of additional set of edges, which we call them links, in order to distinguish between them and the edges of the graph. For instance, here we have a sample input of the problem where k is equal to 1. The black edges are the edges of the graph G, and the dashed red edges are the links. And the goal is to find a minimum collection of links such that if you add them to the graph G, G becomes k plus 1 edge connected. So in a way, we want to augment the edge connectivity of the graph. So for instance, in this input, it turns out that adding only these 2 green edges is sufficient to make the graph 2-edge connected. And an important theorem which simplifies things a lot is one by Dennis et al. In 1987. So it basically says that any instance of connectivity augmentation problem can be reduced to the case when k is equal to 1 when k is odd, and the case of k equal to 2 when k is even. So this means that basically we can restrict our attention to the case where k is equal to 1, which would probably be the tree augmentation problem would have, and the case where k is equal to 2, which can be further reduced to the case where the input graph G is a cactus, and hence we call it the cactus augmentation problem of Hagen. For those of you who do not know what cactus is, well, cactus is a graph that is connected, and every edge of the graph belongs to precisely one cycle. So as you can see here, basically cactus is a collection of cycles that are joined through a tree structure. The state of the art of these problems prior to our work was as follows. So first, we know that APPs start from 2004. There were a long sequence of improvements in terms of approximation factor for this problem, starting from a 2 approximation by Fredrickson and Yaya. Then it was improved to 1.815, and then to 1.8, and then to 3.5. And the best known approximation result prior to our work was a 1.458 approximation by Grandoni et al. In 2018. However, for the cactus augmentation problem, the situation was entirely different. So nothing better than 2 approximation was known, and 2 approximation, there were various ways to obtain a 2 approximation. One of them was again the approach of Fredrickson and Yaya. So the summary of our results is as follows. So we showed that the connectivity augmentation problem admits a 1.91 approximation. The cactus augmentation problem admits a 1.91 approximation. And this immediately implies that the connectivity augmentation problem also admits a 1.91 approximation. So any questions so far? So we begin by classifying the links into 2 groups. So assume this is the input cactus G. Then the first set of links are the internal links. These are the links in which the both endpoints belong to the same cycle. And the rest of the links, we call them external links. And now for the external links, if you start from one endpoint and take this unique path following the tree structure of the cactus, you have this path formed by this imaginary internal links, which we call it the internal projection of the external link. So now we say that 2 links, L1 and L2, are incident if there is an edge, L'1 from U to V in the projection of L1 and L'2 in the projection of L2, such that one of the following cases happen. So the first case is that if L'1 and L'2 share a common endpoint, for example, here, L'1 and L'2 share this common vertex. So this means that L1 and L2 are incident. Or the second case is that if L'1 and L'2 belong to the same cycle, and well, the informal but simple way to explain this is that if you draw the cycle and then the 2 links they cross. So in this case, we also say that L1 and L2 are incident. And what we do is that we use this reduction from connectivity augmentation problem to Steiner Tree. Well, in the Steiner Tree problem, as an input, we are given a graph G and a partition of its vertices into 2 sets, namely terminals and Steiner nodes. And the goal is to find a minimum subtree in terms of the number of edges that spans all the terminals. So now I'm going to show a step-by-step, starting from an instance I of calculus augmentation problem, how we can obtain an instance J of the Steiner tree. So the graph on above with the white nodes is the instance I of the calculus augmentation problem. So first thing that we do is that for any link L in I, we introduce the Steiner nodes with the same label in J. Then the terminals are defined as follows. So if you consider any node of degree 2, for instance, V5 here, we define the terminal V5 with the same label in J. And in order to distinguish between the terminals and the Steiner node, we use this squarish type of node for the terminals. And now we define the edges of J. So the first type of edges are the edges between the Steiner nodes. So if L and L prime are two Steiner nodes, they are adjacent in J if their corresponding link in I are incident. So for example, L5 and L2 are incident, and here we have this edge L5, L2. And the second type of edges are the edges between the terminals and Steiner nodes, which are defined as follows. So if there is a terminal T in which the corresponding node to T is incident to a link L, then T and L are adjacent. And finally, we have no edges between the terminals. So terminals form an independent set of nodes. So the result would be that we obtain a reduction, which from any instance I of the calculus augmentation problem to an instance J of the connectivity of the Steiner tree problem with a set T of terminals such that it satisfies the following properties. So from any physical solution of size alpha for I, we obtain in polynomial time a physical solution of size alpha plus size of T minus 1 for J, and this can be done in the other direction, meaning that any physical solution of size beta for J can be transformed in polynomial time into a physical solution of size beta minus size of T plus 1 for I. Now, a simple observation gives us a lower bound on the size of the optimal solution. So if you consider any physical solution for the calculus augmentation problem, these links that you have in your solution must be the two-edge cover, must be an edge cover for the set of degree 2 nodes. Because otherwise, in the end, you have a node of degree 2, and of course, you have a cut of size 2. So this gives you this bound. So the size of is at least size of T divided by 2. Yeah. So now we have basically all the ingredients we need to come up with the toy approximation algorithm. So assume that Hoff did the optimal solution for the calculus augmentation problem. Then the size of the optimal solution that you have for the Steiner tree instance would be opt plus size of T minus 1. So now if you use any approximation algorithm for the Steiner tree problem as a black box, and then use the reverse direction of the reduction, you will get a solution of this size for the calculus augmentation problem. And then using the lower bound that I showed in the previous slide, this would lead into a 3-row minus 2 approximation. So now what needs to be done is to basically look for the parenthesis approximation factor for the Steiner tree problem, which is an ln4 plus epsilon approximation by Birka, Grandoni, Thomas Radbus, and Lara Sanita in 2013. And unfortunately, for our purpose, this is not enough since 3-row minus 2 is greater than 2. So what we needed to do is that instead of using this Steiner tree algorithm as a black box, we had to basically open the box and modify the analysis a little bit to achieve something better. So any questions so far? So to explain the things that we do, I have to start explaining a little bit of the analysis of this Steiner tree algorithm. So what they do
Should we understand this as you're going to you're not getting better approximation for Steiner tree, but you're getting better approximation for structured Steiner tree.
Exactly. So yeah, so the main idea is that we have this reduction, so we get an instance which is more structured. So maybe you can do something better for this instance. So what they do is as follows. So assume that the optimal solution for this Steiner tree is this 3ST rooted at some arbitrary node. Then they have this marking scheme in which for each internal Steiner node, they uniformly at random mark one of the child edges. So here you can see that, for example, for L4 this H2 from L4 to V3 is marked. Same for L1, L3, and L2. And then they define the witness set of each edge as the set of pairs of terminals T prime, such that the path from T to T prime contains E and has precisely one unmarked edge. So, for instance, here, if you consider E, okay, V3, V9 is a pair of terminals that belong to the witness set of E. So in the end, they are able to obtain a solution of this size, 1 plus epsilon times this expected value of edge of size of the witness set, where edge of n is basically the n formula. And the question is that how we can improve this for our purpose. Of course, we don't improve, as you said, the approximation factor for the Steiner tree problem. So we know that the instances that we are dealing with are more structured than an arbitrary instance. So the first property, which is important for us, is that the instances that we have, we can show that there exists an optimal solution in which the set of terminals is precisely the set of leaves. And finally, the second property is that each Steiner node is adjacent to at most 2 terminals. This is because the way that the reduction moves. And now the idea is that instead of looking at a totally random marking scheme, we change this marking scheme a little bit so that it can basically use the structure of our instance and get a better approximation factor. So our marking scheme is as follows. Again,
do you need really both properties? I see that you will probably need the second property, but the first one doesn't seem very strong.
Well, actually, yeah. Yes, you're right. The first one we're not using. I think the first one you can get it anyway, right? So again, assume that like SC is the optimal solution. Then we route it at some Steiner node which has at least one terminal child. So our marking scheme then would work as follows. So again, consider any Steiner node L. If L has no terminal child, like L1, then we uniformly at random mark one of the child edges, same as what it was before. But if it has a terminal child, like L4, then we just mark an edge which is going to a terminal. Then we have this lemma, which is basically upper bounding the approximation factor. So assume that ML is the child edge of L that is marked. And now we define the cost of L to be this value. And we were able to show that the approximation factor is upper bounded by somehow, if you neglect this 1 plus epsilon and 2 epsilon, by the average cost of the links. So now, from now on, the approximation factor for us is basically the average cost of the links, or average cost of the Steiner nodes. And to prove this, we basically, it's just some algebraic manipulation, and the fact that if an edge is unmarked, then the size of the witness is precisely 1. And the intuition, as I said, is that, well, from now on, the approximation factor for us is the average cost of the links, or the average cost of the Steiner nodes. So, well, now the reasonable thing to do is to find an upper bound on the cost of each Steiner node. To do that, we categorize the Steiner nodes. So, well, we say that the Steiner node L is a good father if it has at least one terminal child. So here L4 is a good father, and any child L prime of L, if L is a good father, we call it good. So, and the reason is that if L is good or L is the root, then the cost of L is upper bounded by h of DL, where DL is the number of children of L. And the reason we say that it's good because for our purposes it's reasonably small. And similarly, we define the bad nodes. And for the bad nodes, our upper bound is different. So for the bad nodes, the cost is upper bounded by h hat of DL, where h hat of n is this value. So this is like a very complicated formula, but what you need to know is basically h hat of n is more than h of n, and it's less than h of n plus 1. So it's smaller than h of n, but not that much. And so the upper bound on the cost of the bad nodes is a little bit larger than the good nodes. And well, so far we established that this upper bound, sorry, it was on upper bound. Okay. So the upper bound on the, so far we established that this upper bound on the costs highly depends on the degree of the node. So if the degree becomes higher, then so does the cost. So basically, in order to show that the average cost is small, then we need to basically identify a set of nodes that have relatively low cost. And this means that we have to identify a set of nodes which have relatively low degree. To do that, we define a set of leaf Steiner nodes as the Steiner nodes that have no Steiner child. So here you can see that L2 and L3 are the leaf Steiner nodes. And since they can have at most two terminal children, then the degree is at most 2. So the cost is upper bounded by h hat of 2, which is relatively small. So h hat of 2 is something between 1.5 and 1.83, so almost 1.7. And we are going for something close to this, so this is really nice. But the thing is that, well, we are caring about the average cost. So if in order for the leaf Steiner nodes to have effect on the average cost, we need to show that the number of leaf Steiner nodes that we have can compensate for the cost of the other nodes. And in order to do so, well, we will be able to show that if you consider the sum of the degree of the non-leaf Steiner nodes, then this is proportional to the number of leaf Steiner nodes, and this is something very simple actually. Yeah. So, well, now the idea is to basically partition the nodes into some groups, such that the average cost per node in each group is small. Then we can simply analyze that the average cost in each group, if it's less than 2, then the average cost of the all nodes is less than 2. And this is an example of how we do it. So the nodes that are in the same color belong to the same group. And the idea is, as I explained in the previous slide, so we know that the number of leaf Steiner nodes is proportional to the number of non-leaf Steiner nodes. So what we do is that in each group, we have only one non-leaf Steiner node. And depending on the degree of that node, we put some amount of leaf Steiner nodes so that the average becomes balanced in each group. Yeah. Okay. So another intermediate step that we have to balance the cost is that, well, the good Steiner nodes have relatively less cost than the bad Steiner nodes. So what we do is that each good Steiner node is responsible to pay some additional costs of its own father by a fixed value P, which we will determine later. And so finally, since the average cost of the nodes in each group, since the maximum average cost in each group is less than is an upper bound on the average cost of all the nodes, then if we show that the average cost in each group is at most 1.91, then we are done. And this is actually true if you set P to this special value. And this is basically all you need to know about this analysis that we have. So as I mentioned before, so when I was mentioning the state of the art I just mentioned the ones prior to our work, because basically after that there was this very nice result by Federica, Vera, and Rico, in which they achieved a 1.393 approximation algorithm for connectivity augmentation problem. Well, this is a huge improvement, and something that is very nice about this result is that, well, they bridge the gap between TAP and the calculus augmentation problem. So before that, in the previous result, there was always a huge gap between the approximability of TAP and connectivity augmentation problem, and this is even an improvement for TAP. And I would like to end this discussion by proposing some open problems. So the first open problem is that can one achieve a better approximation algorithm for the connectivity augmentation problem? So with the recent advances, 4-thirds seems to be a reasonable target. And well, as Fabrizio mentioned in the previous talk, so in all this problem, on all the problem in this area, we have the problem with the door bound. Same holds for this problem. So as far as I know, nothing better than, so it has been only proved that p does not exist. And the factor, I think, is like 1.01. So having a lower bound, which is significantly higher than 1, is like highly appreciated. And finally, so all these problems can be viewed on the weighted setting, in which links the weights. And there the question is that, can one achieve an approximation algorithm of factor less than 2 or no? The 2 approximation, again, can be achieved in various ways, especially this Kamal-Jain algorithm basically is a generalization of all the problems in this area. And they have a 2 approximation algorithm for the generalized Steiner Tree network, generalized Steiner network. Yeah. And that's all.